the gyrator element. In this case, the best example that I can give you for a gyrator element is going to be the electrical motor. So if you have an electrical motor, let's write it down. This is combining mechanical and electrical domains together. But the idea is that if you apply a voltage here to the armature that is between these magnets, this thing will rotate and that shaft will produce on this side a torque and an angular velocity, and then on this side you have the voltage and the current that circulates here. The important thing is that how does this transformation occurs? The equations here says that if we relate the voltage of the on the side is equal to the motor constant times the angular velocity. But you see, here is something worth observing. This one is an effort variable. But this one here is a flow variable. So you don't have the transformation between an effort into another effort like in the transformer, but an effort into a flow, which makes this a type of transformer, but we're going to call it a cross transformer. So you have this equation. But also you have that the current I times the modulus of this is going to produce the torque. So this in here again, this is the flow times the motor constant equals to the effort here. So we have these equations. How in the world do we reduce this to a block diagram or a bond graph model? And what are the causal forms that we have? Because we know that those causal marks determine how the equations are written, so we need to explore that. So in this situation you have, let me just change colors here. In this situation you have that you are coming in and then a variable gets transformed in here with the motor constant in the case of the effort or in the case of the flow. So why don't we just write the two of these? This would be E sub 1, or like in this case, yeah, well, E1, and on the other hand, and here we have I. Yeah, and then on this one here, we have that the effort relates to the angular velocity, which is omega in here, and this is the torque on this side. So you see here is we have to follow the equations. Right? So we have a situation where the angular velocity as an input gets multiplied by by R in here, like this, and this product goes up here, see? That's what this equation does. And this other equation is saying that you have the I times the R equals to tau. So you have the I times the R equals to this. Okay, so this goes like this. And this goes like that. So this is the block diagram of this element in here. But in here you can have, in this particular case, you can have the gyrator element. I'm going to draw it on this side. And of course on this side you're going to have E, and you're going to have the current tau and angular velocity. Tau and angular velocity. Torque, and this is of course the motor constant. So E is caused by this times that. So this is the input. In this case, the input flow. That means, see the input. And then times this is going to be this. So flow omega times the modulus equals to this. So this element can have another type of representation here where the causal marks are in, like here. And here you will have this situation like this. So these forms are possible. So you can have depending on how the equations are written, you can have this form or this form. Or this. In some textbooks, they put this at R prime to indicate was different than this was related to. Any questions about the gyrator? No? This is a two-port element, power conserving. Yeah. But if we were to do it in the mechanical domain or even a hydraulic domain, by now you know that the structure is the same. So one thing that perhaps in closing we could say, if we put this in terms of the bond graph models, you could say that E sub 1 is equal to R times F sub 2. And you see the other one in here, this one, F sub 2 times R equals to tau, the torque. Okay, so this we have the I was just trying to write it in terms of the bond graph notation, and this would be equals to F2, where are we? E1 is equal to R times F2. This F2 times R equals to E sub 1. Yeah, they are intertwined, the efforts and the flows. We just wrote the same equation, and that's not my intent. On this case over here, let's just, sorry about that, let's just do it here. On this is F1 is what we have. This is F1 times R is equal to E sub 2. There you go. These two equations are in bond graph notation these two equations. And those two equations will have this representation.